Hey everyone, how are we doing? I think we got the music stopping. Good. How's everyone doing? Tiffany, good to see you here. Who all is in the chat? Make sure Mewbot is awake. Hope William said bye right there to the class. I missed it. Hey, Kayla, good to see you here. What questions are there? Tiffany, I looked and it looks great. Just sent an email back. I was getting my cup of coffee. But if you have questions now, we have answers. Coffee is here and we are ready to start up. What questions are there? Can we go over Canvas content number 6? Let's do a version of Canvas content number 6 right here. Getting everything organized on the screen. Canvas content, I think it's decision trees, right? So let's get that up and going. Canvas content, a little chill music right now in the background while we get ready right here. Close out that chat. Canvas content number 6. Getting it loaded up. How's everyone's day going? It's been a good morning over here. Pretty relaxing. Sometimes I like to go on a walk before class, but I didn't get to do that today. It's my early days. 8:50, 8 a.m. classes. Not quite 8:10 though, or 8 a.m. That's, whew, when you have an 8 a.m. class, that's not fun. Not fun. But fun is bad, right? 201 knows that. It's funny the things that appear to me good, going well. Awesome, Tiffany. Glad to hear. Let's try out 100 points, make it a little bit better right here. Not that it's going bad, but more points, better day always. Better points, better day. That's what we always say. We got chapter 7 coming up due tonight. And here we are with the Canvas content. Oh, it's due next week. Woo! This is the future right here. Wow, this is a big one. Coming up here, let's preview it. Chapter 10 and 12. Move this around a little bit. Is it due Monday next week? Okay, let's take a look. Good questions. Let's take a look at Canvas content. Yeah, 2C from Lab 5 and 474. We'll take a look at that after. Here we go. Let's hop into doing 201. Let's take a look. So there's over a lot of material right here. I'm going to take a look. This might have to be moved a little bit later into next week, but this is over Decision Trees, Chapter 10 and Chapter 12. So we'll make sure it's due, attempt due October 11th. Make sure to do it by October 11th. I think we'll move it back to the end of next week, because we need to make sure we're through chapter 12 by that point. We did decision trees yesterday. Chapter 10 is, brain's breaking for a second, sampling methods, and chapter 12 is probabilities. They're not that big of chapters, chapter 10 and 12. It's at 1.2. Join the Discord, and get even more. Get up to an extra half a point by joining the Discord and getting those extra points on the Discord. So if you haven't joined the Discord yet, join the Discord. You can get up to an extra half a point. It's pretty easy to get on the Discord. So get those Discord bonus and join in the conversation. Ask questions on the Discord. Decision tree was used to analyze, what is this called right here? Who knows what the name of this thing is? This is the what, which we need for our decision tree. It's some sort of report. What is this called? And we're looking at here at the 4 terminal leaves. Chapter 10 homework, but I haven't gotten brave enough for the quiz. And then, well, you've got 5 attempts at the quiz, so you can always use 1 attempt. We could take a look at it here in a little bit. It's a lot of memorization for chapter 10. Chapter 10 is a lot. Leaf report. The leaves, the terminal leaves of the report. Now, remember when we have a decision tree, I think we've got a whole bunch up in the background right here still from yesterday. Decision trees are going to have these at the very bottom, and these are the terminal leaves. Always number them if you can see them, like first leaf, first over here, and second, third. And you see how I have fourth and fifth all together. And so we were doing some mathematics yesterday, but this right here, if I shrink it down a little bit, are the 4th and 5th leaves of the leaf report. And you can see the information like 144 right here is how many people total there are in leaf number 4. Like 109 plus 35 is 144, and that is the total people. So if you number the leaves across 1, 2, 3, 4, 5, and you go to leaf report, you can see the same 1, 2, 3, 4, 5. Like leaf 2 is very tiny, only has 21 people in it. Remember, this is leaf 2, and you can see here there's only one person, and we were looking, I think, if they're in a fraternity or sorority, and this would be the one person who's in a fraternity or sorority. The 20 other people, which are the red ones right here, are not in a fraternity or sorority. Example from yesterday, but important to know what we're looking at right here. So I want to point this out, and I think a lot of people get confused on this. The yes, no is the what variable. This is where people get confused a lot of times. The yes, no right here, we're asking, do you use a reusable water bottle? The yes, no, if you see this right here, is the what variable. The yes, no right here is the what variable. We're asking, do you use a reusable water bottle? 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 Do you use a reus Reusable. It is categorical. It is categorical. And so we got another set of variables over here. Why is there like variables over here on this side? And then we have a variable over there. It's a little bit reoriented to how we might think they would be. But the yellow ones are the what variable, and the green ones are the what variables. So the yellow variable, like we're asking, do you use a reusable water bottle? That's the variable of interest. That's the question we're asking. So the yes, no, and it's important to know how to read this, is the what variable right here. It is categorical, but what position is it in? Reverse it. You're right there. This is the y variable of interest. That is the y variable of interest because we're asking, do you use a reusable water bottle? So those are the y variables, and then that makes the other ones the x's. These are the x's that would explain if somebody uses a reusable water bottle. Does that make sense right there? Cliff throws some 50 points. Good job, Cliff, right there. So we have right here, and great job, Kayla and Tiffany. We have here the x variables and the y variables. I think a lot of times we get confused with this output, like where's my x's, where's my y's. It's a little more easy to see. Green is the quant. So this is categorical because do you use a reusable water bottle is categorical. This over here is quantitative and categorical in some ways. He's Mewbot. Sleeping on the job, Mewbot. What you doing, man? Wake up.
I am Mewbot.
You owe people some points, Mewbot. You've been bad, Mewbot, today. You chill out there, Mewbot. Thank you so. And Colin, everyone say congratulations to Colin. If you want to put your big news in the chat, you can. I think you can say it. I think you can. But Mewbot, where are you? Scooby-Doo, where are you? I was never a fan of Scooby-Doo. I'm sorry. A pup named Scooby-Doo is a pretty cool show. It's more funny. Like, is age quantitative or categorical? A decision tree can be used for both categorical and quantitative variables, correct? Exactly. Because notice right here, and I'll show you with this. Here's my thing. You have right here the following. You have this variable, which is an x, which is quantitative. You have these variables, which are x's, which are categorical. So within your x's, you actually have quantitative and categorical, exactly. But every single one of those I've highlighted in green is an x variable because it's explaining why people use a reusable water bottle. So of group 1, if we go here to group 1, and we put a little 1 next to this, these are people who are female and have broken a bone. Of the people who we'll be sharing, awesome, I'll let you share it right there. Yes. Yep. Whenever you share, we'll put it out there. Yes, I'll let Colin share his news, and then it's really cool. And congratulations again, Colin. So of the people who are female and who have broken a bone, 150 of them use a reusable water bottle. Of the people who are female and have not broken a bone, 176 of them use reusable water bottle. Of the people who are male and are less than 20 years of age, 83 of them use a reusable water bottle. Of the people who are male and 20 or greater, 95 of them use a reusable water bottle. That's what we have with that info right there. That's what all that means. So now we know what this means. What percent of females? Now, this is where it gets confusing. Females are people in Leaf's what or what. Females are people in Leaf's what or what. Females are people in Leaf's what or what. This is where people are like, how would I possibly know this? Females are people in Leaf's what or what? Drawing on the output helps. Females are people in Leaf's what or what? Females would be the people in Leaf's what or what. I've numbered my leaves so I can be like, oh, well, they're in these leaves. The top two leaves right here. So can you see how many females use a reusable water bottle? Because all of these leaves right here are people who are female. So how many of these people use a reusable water bottle? How many would be 150 plus 176? That's how many, and I can't do my R tricks right here. That's how many. So that is just how many use a reusable water bottle. And then we need out of the total, which is going to be not just these numbers, but we're also going to divide by the people who don't use it. And so there we go right there. And that should solve it. And I'm going to cheat. I'm going to go here to R. And that's why R is beautiful. Does this make sense right here, what we've done? I've just taken how many total people there are. I love R for this reason. So I can show you just clicking on the screen right here what's going on. This is how many females use a reusable water bottle, and this is how many females there are total. If you're looking at it visually, it's going to look like this right here. The total is every single female, because we're just adding up these amounts right here. And then how many of them do use a reusable water bottle is the, I think Tiffany, great job right there. Another 50 points, Tiffany, is the 156, right? Or the 326. So that should be good right there. Is it how many or what percent? Is it 326? So what percent? So we want the percent, so we have to do it mathematically right here. We have to grab this. And then it wants it as a decimal like this. So we need to go here. And it says round to 2 decimals. Well, that rounded up, didn't it? That should be right there. Be very careful. Be very careful. If you see something off by like 100th or something, let me know when you take your test. When doing decision trees, categorical variables with more than 20 levels should be... Oh, you should know this one. When using decision trees, categorical variables with more than 20 levels should be what? Categorical variables with more than 20 levels should be what? Now, we can't see the answer on the screen anymore, but I want you to think about what the answer would be. Categorical variables with more than 20 levels should be what? Not used. Yeah, we're not going to use them. They'll act like identifiers, so that's a no-go. We can have categorical Ys, categorical X's, quantitative Ys, quantitative X's. We'll put in a ton of X's. We'll have one X, one Y, but we're going to focus in on not using things that are identifiers or things that act like identifiers. So that's a no, not be used. A researcher wants to examine the grams of fat in milk. They separate milk into groups: whole milk, 2%, low fat, then randomly select cartons from each of the groups to measure the grams of fat. This is an example of what kind of sampling? So we have 4 key terms right here, and we're going to define all of them really quickly right here. The most confusing one, which is one of the answers, is going to be between cluster and stratified. Oh my gosh. Calm down there. Mubot, are you revenging on us? Oh, that's weird. Okay, so let's go with the easiest one to start. It's going to be simple random sample. The first step to a simple random sample is 1, everything is given a number. 2, numbers are selected at random for the sample. So a simple random sample is pretty simple to do. Can't delete that little thing right there. So a simple random sample, everything is given a number. Then we simply select those numbers at random. And yeah, does that make sense? It's just, you just say everyone gets a number. And we're just going to draw numbers out of a hat. That would be a simple random sample right there. You just give everyone a number, shake up the hat, pull out a number, simple random sample. The next easiest one to talk about right here is going to be systematic. Now, one detail that we usually forego in systematic is start at a random starting point. This is slightly important. Reason being, if you do this multiple times, you don't want to start in the same spot because there could be some systematic order to the sampling or like to a problem. Think about like a roller pin that has a problem every 5th. So if you're on the 5th observation, you sample every 5th. We'll talk more about this in a second. You would see that problem every time, but if you're off it, you wouldn't see it. So, or if like something wears down over time, you might see the time order effect to it. So we're going to pick a random starting point. We're going to say we're going to go to the library, and then we generate, pick a random number between 1 and 24.
That would be 9.
So we're going to go there at 9 a.m. I'm going to go to the library at 9 a.m. I'm glad it was military time right there. I'm going to go to the library at 9 a.m. and I'm going to talk to every 10th person who walks in the library. So you pick a random starting point and then sample every kth observation. So in this example right here, when I said sample every kth observation, Brian says he's going to sample every what person at the library. So once again, here I'm going to follow the process again. I'm going to do a simple systematic sample at the library. Pick a random number between 1 and 24.
It's 8.
So I'm going to go there at 8 a.m. and I'm going to pick every 20th person at the library. Usually you want to pick something that spaces out across the interval. You don't want to pick like every second unless you have like a very small, then you're sampling every other thing. But the kth you're choosing is a placeholder for what you're choosing every 5th or 10th or 20th. So So you just say no, 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 yes. If you're choosing every fifth, then no, 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 yes, and you choose the fifth. You just go through there and pick every fifth item that goes through. Like you're like having things go through a conveyor belt. You just say no, 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 yes, and you pick it. This is a perfectly fine way, and this is random, but you have to watch for a time order effect, which is kind of a additional thing to consider. Now we get into the two we're going to be picking between, which are the ones people usually confuse, which are cluster. Would this be systematic every? Yep, and technically it should say from a random starting point. Usually, like I said, sometimes we forget to mention that, but that sounds very systematic to me because every 50th person is being asked where they live. This would be an example of systematic. Great job right there, Tiffany. That is going to be systematic because it's every kth observation. Technically says it should say a random starting time is chosen, and every 50th person at Dollywood is asked this question. That would be better systematic sampling. So the other two we're picking between right here are cluster and stratified. And these are the ones where people get them wrong. Oh my gosh. I cannot tell you that it drives me crazy that about 50% of the time people get these wrong. So let's set down what clustering is. Clustering, taking a whole bunch at once. So, cannot make that more clear that clustering is taking a whole bunch at once. So, items are put into groups randomly. They're put into groups randomly. That's key right there. Select groups of items at random. Perform a census on the whole group. And that's going to be one of the key deciding factors when we look at this. Write these down as steps to know which sampling method you're using. We're pretty much going through a whole lecture right now by talking about this, but clustering is taking a whole bunch at once. You're going to take a whole bunch at once, and you're going to do a census on that group. You'll see why that doesn't apply to one of these coming up. Stratified is going to be acknowledging a difference and sampling according to it. Should you, if you want to talk to UT students and you want to find their views on an issue, should you talk to more graduate or undergraduate students? If you want to talk to UT students and find their views on an issue, should you talk to more graduates or undergraduates? Now, I'm not saying don't talk to a certain group, but which of them would you talk to more of? If you want to talk to UT students and you want to find their views on an issue, should you talk to more graduates or undergraduates? Should you talk to more graduate students? You want to find what do UT students think about this? Undergraduates. So are we doing clustering? There are more of them, exactly. So does this sound like an example of clustering or stratifying? So does this sound like clustering? I'm throwing 100 points out there. Does it, with what I'm talking about, does it sound like a clustering example or a stratifying example? So just read the definitions I have on there and be like, okay, we want to figure out the views of UT students. So should we cluster based on undergrad or grad, or should we stratify based on it? So do you think we should cluster or stratify? Don't worry. Just read over what I have on the board so far and then think like, okay, should we be clustering or stratifying this? We're going to stratify because we're doing what? We are great job right there, Kayla. Excellent work. We are acknowledging a difference. So what does it mean to acknowledge a difference? Right here, you're saying, okay, wait a minute. I've got graduate students and undergrad students. They're going to be different in some way. Like maybe we're asking, what do you think about parking? And you're like, well, everyone hates parking. True. But graduate students might be more likely to drive because they're more likely to live off campus. So you're going to maybe, if you get too many graduate students, you might have a totally different view than what the general population's. You realize there's a difference in exactly. And so because there's a difference between, like, these two groups right here have differences. Now, another key thing we're going to not do, exactly. And then what are we not going to do with our graduates and undergrad? Like, if you think of them as clusters, what must you do if you say, okay, I'm going to pick undergrads? If we said that we're doing clusters, what would you do? And what's a census? What would you do if you said, let's cluster by grad, undergraduate? You would say that they're put into groups randomly, which doesn't apply to grad, undergrad. Those are not random groups. You're going to select groups of items at random. Like you're going to select the undergrad group at random. Be like, okay, let's choose undergrads. And then you're going to speak to every single undergraduate student. And this would not be representative of UT students anymore. So if we stratify by something, we're going to first start by putting things into groups based on a difference. This is the key part right here. It still deals with groups, but now they're purposely separated on a difference. Does that make sense? Like in stratified, the difference is the key factor. Like, okay, we're going to stratify based on grad, undergrad. So we're saying there's a difference between these two groups. They're not randomly put into these groups. So now we go here, and now we say we're going to sample using or use simple random sample to sample groups. Sample each group proportional to its population size. Sounds more complicated than it is, but let me ask you this. If we have 10% graduate students, what percent of your sample should be graduate students? If UT's population size of graduate students is 10% graduate students, just hypothetical. Someone says it's not. I say, oh, it's hypothetical. Hypothetical 10% of the UT population is graduate students. What percent of your sample should be graduate students? So when you go out and you start sampling the graduate students, they should make up what percent of your total sample? Because 10% of UT is graduate students. So you're going to say, well, I'm going to go out and my sample will have what percent graduate students? And you're sampling from that strata. Strata means layers in Latin. So you're going to that layer, that group, and you're sampling 10%. So you're not taking all the graduate students, because if you said, well, graduate students is a cluster, they're a group. Well, they're not randomly put together, and you're not going to take all of the students who are graduate students. Don't do that. You're not clustering on graduate, undergraduate. You're stratifying by acknowledging a difference. So let's take a look at our question. A long way to talk about this one. But it says right here, they separate the milk into the groups, whole milk, 2% and low fat, then randomly select cartons from each group to measure the fat. So is this strata or cluster? What do you think? This is where a lot of people... What do you think? Is it strata or cluster? Because it's not simple random sample. I'll wait for all the answers. And throw some points. Why is it which one? This is the tough one. Why is it which one? I want you to make an argument. I'm not kidding. This is where people, it's a 50. Yeah. I'm not kidding. Like when I put this on this thing right here, it's people get these wrong about 50% of the time. It's like people are like, I want you to look at some of the key characteristics right here. So let me put the key characteristics. I want you to identify a key characteristic that it holds or does not hold. This is where people lose points on the test. So I want you to start identifying the key. Okay, I think it's cluster because they selected groups. Random. So if you were to buy milk, I think you have kids, right? So because this is in the picture too. And I think you told me. If you were to buy 2% versus whole milk, would your kids think that was random? Listen, this is random too. Would your kids be like, this is random. The 2% is randomly put there. So if you were to buy 2% or whole, are those just randomly put into those groups? Like 2% is in a random group and whole is in a random group. Well, so what I'm saying is you put all the 2% into one group. You put all the whole milk into another group. You put all the low-fat milk into another group. You got three groups right here, right? You got whole milk, 2%, and low-fat. And you say, I just put these into groups randomly. It's not random. It's not random. Don't worry. This is where we're just like making sure we see it. It's not randomly put into groups. Well, they are in different groups, but you are whatting with the groups right now. What are you doing with the groups? I want you to see it. I could say it, but I want you to see it. What have you done by saying whole milk, 2%, and low-fat milk? What are you doing with those groups right there? HTC, great job, HTC, 50 points. What are you doing with those groups of milk right there? What are you doing? This is what I want you to see and what I want you to say when you look at it on a test. And you're like, oh, we're doing this right now. We're doing this between the milks. You're segmenting correct, but you are correct. And then use the definitions I have on the screen to be like, oh, I'm doing what with the milks? I'm definitely doing this. But so you are, look at the definition on the screen. I want you to see it. One of these things, I don't want to point directly. I want you to kind of be like, let me see. So when I'm doing 2% whole fat, kind of look at the very start of the definitions. You'll see it, I promise. You are doing what with the milks by separating them into these groups. They're not put randomly into groups. I think Kayla sees it. By saying whole milk, 2% and low fat, that's definitely doing what between the groups? Yeah, you're acknowledging a difference right here. You're acknowledging a difference between the groups. You're like saying, okay, these are different in this way. And then you're not taking all the 2%. You're not taking all the whole milk. You're not taking all the low-fat milk. You're sampling random. Look right here. Put them into groups based on this difference. So we're putting them into groups based on this difference. Use a simple random sample to sample the groups. Then randomly select cartons from each of the groups to measure the fat. So that's going to be using a random sample. They don't mention that they're doing it by the percent of the population right here. So they maybe should say like in accordance to the population percentages for which they account for. But we're not taking whole groups right here. If this were a cluster, you would take all of the whole milk. Like it would say like, and select one of the groups and do a census on it. The census part is probably one of the biggest keywords you will usually see when we do a cluster question, is that we take a group or at least groups and do census on them. So if you do see a census on one of these questions where it says like select the groups and then do a census of the group, that is almost a key indicator that it's going to be cluster. If you're seeing that we're sampling randomly within groups, then we're probably acknowledging a difference here, like different types of milk. This is, like I said, about 50% of people get these questions wrong. So hopefully this saves you on the test and it's not like a 50-50 guess, because a lot of people get those wrong. The concept of, yeah, we can probably do another right here. I think so. I'll see if we can find another one. We'll see if we find like a cluster one. It's good stuff. And then we'll do Muhammad's question here in a little bit. The concept of population is key to inferential statistics. Yes, inferential statistics means we're taking samples, because statistics comes from samples, and making inferences about populations. It better not be reversing that and be false. In probability, the value of each trial is called a consequence. No, it's called the outcome. In probability, the value of each trial is called the outcome. I don't love that question. Wait, false. What am I doing? The consequence. I don't like that question. It's called the outcome. At each trial, we note the value of the random phenomenon and call it an outcome. I think it's talking about I don't even think that's a word we use, the consequence. Better be false, because I was like, I don't seen that before. Question trying to trick me. We're updating the question. Submit the quiz. Better get that 10 out of 10. Woo! 10 out of 10 points. Tricky last question right there. Trying to trick me with that true false right there. Let's go ahead and preview it one more time. We'll see if we can get another version of this. Oh, we got the whole low-fat milk again. These are fun. I'm going to try to find another systematic random sample one of sorts. So we can do that. Can we do the random question when sample has characteristics which correspond to the character of the population the sample said to be? So think about this. If our sample looks like the population, I don't want to say it. If our sample looks like the population, then what would it be called? If our sample looks like the population, we would say our sample what's it well. Might see that one on here. Trying to get another I'll give one more try out here and see if we can get one with a sample systematic cluster. It is. Yep, it represents. Good job, Tiffany. Excellent work right there. Be representative. Really? We might have to do some chapter 10 at some point to get another cluster versus, well, looks to be the only one. That's really sad. Okay, let's do 2 or 3 more questions, and we're going to hop to Muhammad's question right here. So here we go. Let's see what we get. We've tried a few times to get some good questions right here. Suppose, I can't solve them all. So we'll do a few more right here. I can't solve all of them specific to one person's quiz. Here, we'll see. If we get that one, Tiffany, we'll do it right here. You ready? Let's check out and see what we got. So luck of the draw. And remember, this isn't due for a while. So, yeah, you're welcome right there. So let's see right here. You ready? When doing decision trees, we got this, should not be used. A decision tree uses multiple X's, true or false. You got this right here. You got this. So here, I'll do it after this one. I'll do it after this quiz. A decision tree uses multiple x's, true or false? A decision tree uses multiple x's, true or false? This one we should get like that. Boom, this is true. Decision trees uses tons of x's and uses how many y's? This is something we went over a lot yesterday. We were like, decision tree uses tons of x's and how many y's? Decision tree uses tons of x's and one y. The sample frame is the list of all possible outcomes. So we have what's called a sample space and a sample frame. And these are two confusing terms. So let's write them down right here. They're two different chapters. So we have a sample space, and I'll do the question, Tiffany. Thank you, Tiffany, very much. And sample frame. Okay, so sample frame and sample space and sample frame. Okay, so a sample space are all possible individuals we could sample from. If I go to UT Library and I want to talk to students, exactly. If I go to UT Library, like right there, Kayla. If I go to UT Library, the sample space would be any student who's in the library because I could possibly speak to them. The population is everyone I want to understand, or everything I want to understand. All possible items we could sample from. If we're not doing people, because we could do widgets or something. So the sample space is all possible items we could sample from, the population, and then we get down here to the sample. The sample is what we collect data on. And this is for chapter 10 right here. The wording's going to change for the next chapter. So this is chapter 10. And this is sampling, which we'll be doing next class. Chapter 10, sampling, there's key definitions. The population is everything you want to understand. The sample space is everything you have access to. So this is all things you have access to. This is probably the one that people really get wrong all the time. So I'm going to put it in red right there. That's the one people forget, is because it makes sense. The sample is what you collect data on. Population is what you want to know. The sample space is what you have access to. Am I reversing these? Sample frame. Sample frame, my gosh. Okay, we'll make sure. Sample space. Sample space, I reverse them. Sample space is going to be all possible outcomes for probabilities for events. So this one's a little bit different right here. I was like, I did reverse them, didn't I? See, we make errors. So when it comes to a sample space, if I were to ask you, oh no, Kayla, right, change it. Pull out that eraser. If I were to say I have 2 coins and I'm going to flip them, this is types of question you'll see with these. What's the sample space for the outcomes of the coins? So I'm going to flip them twice. I'm going to have 2 coins, not flip them twice, but I'm going to have 2 coins. I want to know the sample space for the outcome of the events. So what could happen when I flip 2 coins? I could get tails, heads. Can you think of another outcome that could occur and that's in the sample space for all possible outcomes of events when you flip a coin twice or flip 2 coins? What's another possible outcome for events right here when you flip 2 coins? What's another? Just put in the chat like TH, heads or tails. Well, so we could get heads or tails on 1 coin and we're flipping 2 coins. We're going to go flip, flip. Great job, Tiffany, right there. I think you've worked ahead. 100 points, Tiffany. Tiffany wrote down the full sample space right there with heads, heads, and tails, tails, and then also if we go by order right here, heads, tails. So this would be the sample space. So weirdly shaped coins right there. Does that make sense, Kayla? I think Tiffany sees it right there. So if you've done chapter 12, you can see what is called the sample space right here, which is all possible outcomes of events when you flip 2 coins. So are all of these equally likely? Yes. But let's talk about kids for a second right here. If you think about the probability, and one of the chapters goes over this, real quick question on this, and then we'll do Tiffany's question, then we'll hop to Muhammad's next. Like if I were to say to you, what is the sample space for having boys? So let's say you have 5 kids. So your kid will either be a boy or not a boy when you have a kid. Is it equally likely? Like, are all things equally likely? Like, think about this. Let's say 10 kids. Let's go crazy here. 10 kids. So is 5 boys as equally likely as 10 boys? Yes or no? And just think mathematically, just think logically here for a moment. So you will either have 10 boys, 9 boys, 8 boys, 7 boys, 6, 5, 4, 3, 2, 1, or 0? And is 10 boys as equally, if you have 10 kids, is having 10 boys as equally likely as having 5 boys? Just think how it would work. That, what's more likely? Is it, well, there is the outcome you have 5 boys, but think about this. The only way to have 10 boys is that every kid's a boy, right? 5 boys would be more likely than 10 boys because the only way to get 10 boys is that every single child's a boy, which is pretty unlikely just probabilistically that every child will be a boy. So 5 boys would be more likely than 10 boys. Now this one up here, if I change the way the sample space looks and I draw it this way, and I say like this right here corresponds to you get a tails or a heads, then these events right here have a probability of 25% each. And the top event has a probability of what? Because it could be tails, heads, or heads, tails is what I'm saying. There's 2 ways to get this. And this goes a little bit more complicated on it, but the probability, and you can solve it mathematically. So the probability of heads, heads is 25%. The probability of tails, tails is 25%. The probability of getting tails, heads in any combination now must mathematically be what? So it's two combinations of all the sample space, and we've kind of made a smaller version of the sample space here, 50%. So the sum of the sample space must be 100%. So we're seeing that, and you can solve that by rules of the complement. It's kind of a big overview of the chapter right here. We did a few probability rules, and that might actually get into Tiffany's question right there. We'll finish off this quiz, and let's see what the question was asking. The sample frame is the list of all possible outcomes. I think it's trying to trick us right here. This could be the one I get wrong. Haven't gotten a thing wrong Canvas content all semester, so let's not do this. The sample frame is the things we can sample from. So I'm going to be really mad if this is true because that sounds a lot like the sample space to me. And that's a tricky one. So this is the sample space is the list of all possible outcomes, and the sample frame is the list of all things we could sample from. Very tricky question. I think we've done it correctly. The blank is a list of collection of... Oh, what do you think this is? Wow, I'm so glad we got these back to back. Really drawing the contrast right here. The blank is the list of all possible things of individuals from which the sample is drawn. So what do you think this is? Good definition questions right here, and so glad they're back to back. The blank is a list or collection of things from which we draw our sample from. So what is this going to be right here? Is it the population, all people, or things we want to understand? Is it the sample, which is the thing we take from the sample size, which is how many we take? It's going to be the sample frame. And just think about like making a picture frame and taking from within that picture frame. The sample statistic is the metric we calculate from a sample. So yeah. You are at the law of large numbers casino. That's what that stands for. On spring break, you play their game right here. Each wheel has 10 equally likely spaces with 4 skulls, 3 lemons, 2 cherries, 1 bell. What is the probability that you get a lemon and a cherry and a bell? So in that order. I probably need to tell Terry to make sure it says in this order. So when we do this right here, we're actually doing the multiplication rule. To say that you get first a lemon is 30%. Because there's 10 spaces, 30% probability of lemon. Probability of a cherry then is 20%, because, what are you doing to me, computer? 30% times 20%, this is the multiplication rule right here, and then a bell is next, so it's going to be a very small number right there. And this is the multiplication rule because the wheels roll independent of each other. So in this order, what is the probability you get a lemon and a cherry and a bell? Not talking about permutations of them that exist. And then enter in a decimal right here. I think we've done it properly. Submit that quiz. Tell me that 10 out of 10. Ooh, 10 out of 10. Ooh, what happened? Did I enter in an extra decimal? Are you kidding me? Oh my gosh, I did it. First error of the semester on a Canvas content. I entered it. If you saw my mathematics on there, you could see it. It's 30% times 20% times 10%. I threw it in. You missed the last one because you did 4 instead of 3 exactly. So be very careful. The last one, if you review the tape, I moved my decimal over 1 spot. That would be wrong, and I would lose points. I tell you what. First error Brian's man on Canvas content. We're throwing out a crazy 500 points. If you were here for that error, you get some crazy points for that. It happens, and that means you got to retake it, and you got to be careful with those decimals because that's a factor of 10 error. Oh no, I put in 0.01 instead of 0.1. And the reason it's 0.1 right here is because it's 1 out of 10. I was like, oh no, what did we do? And that was an error. Don't get caught with those errors. Whoop right there, 500 points. My mistakes are your prize. Let's hop back over here. Oh, and then Tiffany's question. Tiffany's question is, let me put on all chill music. Oh no. Suppose event A is taking 15 or more minutes to get to work, and event B is taking less than 15 minutes to get to work. What is a complement? A complement is either A or not A. So think about this. If we talk about what a complement is, something in its complement adds up to 100%. So you either have that you take 15 minutes to get to work, or you don't take 15 minutes to get to work. So think about a complement with class. You either make an A in the class or you don't make an A in the class. You either pass the class or you don't pass the class. So when you have a complement, if I tell you there's a 70% probability you make an A, what is the probability of not making an A? So solve this real quick mathematical question. There's a 70% probability of making an A. What is the probability you do not make an A? So 70% probability you make an A. What is the probability you do not make an A? 70% probability you make an A. What is the probability you do not make an A? Again, Muhammad's question. There you go. Can we take a look at 2C? 30%. Yep. And so complements are, so I don't want to say true or false, but I think you can figure it out. Complements are like either something happens or doesn't happen, where you have the 100, like either this will happen or this will happen. There's no overlap. You either make an A or you do not make an A. So if you don't make an A, then you can't make an A. If you make an A, you can't not make an A. Does that make sense what complements are? It's like the other side of it. Like the remaining portion of the pizza you do not eat when you order a pizza is the complement. I think you're on the right track, Tiffany. It complements you. Yeah, exactly. It's like it's the complement. It's like you eat part of the pizza and you say I ate 40% of the pizza, 60% remains. It's the portion of the not ate pizza. So you eat pizza or you don't eat pizza. And just think about that with probabilities. Like something either happens or doesn't happen, and the probability of it not happening is the complement. It's like yes, no, and there's no overlap. Either happens or does not happen. It's dichotomous events, as we would say. And that's what a complement is, and it's with an E, not an I. I'm usually like, everyone here looks great today. That's a complement with an I. But a complement with an E is the remaining portion. Said 2, grabbing your question, Mohammed, was 2C. So we're going to do 2C here, for like how I eat my husband's food. Just say, I'm finishing your compliment. Just say, I don't want there to be any compliments. So let's take a look right here. I think the item frequency right here. Here we go, hopping into it. 2C for Lab 5. Let's take a look. Okay, so we have right here, I'll say compliment. I'm just complimenting you. The item frequency right here, we're looking at carts. We're looking at more food items right now. We've got the data already loaded in. So make sure you have the transaction data ready to go. I think all the code is supplied above. And it's pretty neat stuff we got going on right here. I got some crazy code going right here. Don't do this. Bad idea. Bad Brian. Do not print that or do not knit that. Aw. So these transactions right here, we're actually looking at what people bought from grocery stores. Oh, I just did it again. I literally said don't do that. Okay, we'll stop it. Let's look at the first 5 carts right here. Remember, inspect goes inside of it. It's not really a grocery store. I think it's like a little nice place, little cafe or something. And we have the first person bought an apple pie and a ganache cookie. The next person bought a coffee eclair, apple pie, almond twist, and hot coffee. So this is what these people are buying from their market, little cafe or something, and we can see what the people are buying. Now, what we want to do is we want to take this transactional data and we want to view it in ways to see things like what are the most common bought items, because these are just like, this is like, it's for 201. I hope this makes sense too. This is the first person who came to the store and is like, I'm going to have an apple pie and a ganache cookie. Next person comes to the store, they're like, ooh, coffee eclair, apple pie, almond twist, and a hot coffee. Maybe they're buying for 2 people. Maybe they need 2 hot coffees then. But these are the items that they are buying when they walk into our cafe, and we have 75,000 transactions right here. So then the question becomes, well, what are our most bought items? And we need a code right here called item frequency. Item frequency. And item frequency is going to show us the frequency of the items bought, which is also known as the support. It's just a fancy word to say what % of the time are the items bought. All we're putting inside of here is the transaction data. Remember, this is just transaction data right here. And we're putting inside of a function called item frequency, so that it shows us the frequency of the items. It's not going to look so great here, but we're going to fix it up. So it gives us the frequency of the items. Probably the best thing to do to this is to immediately sort it. By sorting it, you can see down here the most bought items. So now it's sorting it from least bought item to most bought item. So pretty nice and neat. We can see our coffee eclair is the most bought item. So 10% of our customers, or 11%, really close to 11% of our customers are buying a coffee eclair. If it doesn't look pretty to you yet, we could times it by 100. We could also go inside of here and round it. And it's going to round it to 2 decimals. Let's see what it does by default. Oh, that's a hard round. Let's go to 2 decimals. And now we can see 10.92% of our customers buy a coffee eclair. So this is kind of what we want to do with coding and why we like coding. If you're a 201 student saying, oh, that's kind of neat right there. We could look at it another way, though. We could simply take the probability and multiply it by the length of the transaction data set. It looks like I'm missing a parentheses. It's mad at me right there. And if we multiply by the length, what do we get instead now? We actually get how many people bought this item. 8,193 people bought a coffee eclair, which represents 10.92% of our individuals who walked into our store. So we can get some pretty good information on this pretty quickly, like how many people bought it or what percent of people bought it. And even better, probably one of my favorite things, which I swear I didn't know for a long time, is we could go right here to this and we could select just a certain thing and look at just the percent of people who buy hot coffee. So lots of quick ways to get the code to the answers we're looking for and say, well, what percent of people buy a hot coffee? Or what percent of people buy a vanilla frappuccino? We could actually get multiple items here. And this is just how to use the output we're working with right here and get certain items. Ooh, it does not like that. Oh, didn't close it off. There we go. So with this, we can get certain answers to what percent of people in our store bought these certain items. And look at how we build the code. Please note how many times I ran my code. Don't just try to copy the code. Go through the steps of building it and changing little bits at a time. That's what we do right here. So what we need now is an additional code right here to find out the percent of people who are buying all of these items. I want to make my life easier by taking these items and storing them as items right here. So it's now a character vector of items. It's very similar to what I made right here, but I'm storing it outside so I can kind of deal with it as its own object. So literally, this is just the 3 items we're looking at. So when I go here and look at these cards, there is a library we need to have running. It's already running for me, but the A rules library has inside of it certain functions we need. And let's go here and create a subset. And we want to subset what? We want to subset our transactions. And with our transactions, we want to go here to item. I did it earlier today, and I'm trying to remember. We'll try item. Equals, or no. Yeah, 5B. Yeah, let's go 5B next. You got it. Percent AIN percent. Please note it changes colors. Might be hard to see, but that's a small color change telling you this is now a certain special type of code. It's item equals, or percent AIN. I'll mention what percent AIN percent means. It's mad about that. It's items. There it goes. 17 transactions total. 17 transactions. So we could solve this mathematically. We could store the subset. And let's talk about what percent IN percent means. When you do the subset, the first argument is what are you subsetting? I am subsetting my transactions that people came into my store and bought stuff. The second argument is what are your conditions? Now, this is something inside the items right here is used inside of A rules to select the items inside of the cart. And it's saying it must contain all of these items. All these items, the AIN, I always remember all in. So all these items must be in the cart. And what items all must be in the cart? The green tea, the vanilla meringue, and the hot coffee must all be in the cart. Probably one of the best things to do here is go to inspect and inspect your subset. And what do you notice about cart 17 right here? Vanilla meringue, green tea, hot coffee. The carts must have, and ooh, is this the one cart that bought only those 3? Good for them. And it can have more, but it must have all of these items. If we did IN, it could be any of these items. And that's going to massively change our subset right here. You see, it's a much larger subset because now we're getting a subset of carts that have in it green tea, vanilla meringue, hot coffee, and it can have just one of those items. Like this just has vanilla meringue, and that's the difference between IN. It just means it has one of these items. It could have all of them, one of them, 2 of them. It just has to have one of those items. But AIN has that we need all of those items. Just remember the all in. So that's why it's much smaller. These are the carts that have all of those items. Now, they can have more items, but they have to have all 3 of those items. To be selected for this subset, you have to buy all 3 of those items. And so let's take a look. So that's how to do this one right here, how to look through. Good stuff. Peyton, good questions. Let's put on a little serious music right here. Do some 5B. Drink some coffee. Good stuff. Got lots of time. Quick question for the coding night. Is it okay if I put problems from the homework and labs in my notes? That's 100% fine. Steven, thank you for asking that. 100% fine. Your notes are your notes, and you can go through them. Okay. Let's take a look at 5B right here. Here we go. This is 5B for lab 474. Let's interpret lift first. Find the overall probability frequency that cherry tart appears in the data. It's support. Okay. So one of the easiest ways to do this is go to item frequency of the transaction data frame. And we're going to go right here and we're only going to select cherry tart. So remember, item frequency is a named vector and we can get the frequency of cherry tart. And can we store this? GTFREQ. And that'll be a named vector. Cool. Name vector just means it has a name at the top of it. We're good on that. Second, remember that the lift tells you the factor increase. We talked about lift today. Lift is going to be a factor increase to the native probability of what something was. So when you look at the lift of something, we're talking about the probability of watching Squid Game is 20%. But if somebody watched Black Mirror, it increases to 80%, which is a lift of 4. So the original probability of 20% is lifted by a factor of 4 to 80%, which is the confidence. So that's how it changes the native probability. Second, remember, blah, 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 times more likely, given that the transactions are applied by random chance. Fully interpret the value of the list, include a reference to the probability that card had cherry tart before and after knowing the left-hand side. So which rule are we looking at? I've jumped kind to a longer part. Which rule? Remake the association rules so that the support is at least 100 cards. I'm changing my volumes. Confidence is this, min length is this, left arrow. So we do have our rules from earlier. Check out class today. So here we are with where we made the rules. Let's go down to here and remake the rules so that the support is at least 100 cards. Good. The confidence is at least 50%. And we need min length and max length. So is it min len? I'm gonna cheat and look at the a priori. I think it's min len. Min len. Let's double check. There it is, min len and max len. Easy to make mistakes on those. Make sure we get them right. Min len and max len. So for the minimum length of the rule and the maximum length of the rule. So it said minimum length is 2. Wait. The maximum length is 2. So max len is 2. A lot of arguments to remember, and sadly, it doesn't show us. It doesn't show us it in the. I don't know why the help would not show us that. The maximum length is 2. The left arrow, the result into length 2. Length 2 rules. So rules of length 2. Remove any redundant and not statistically significant. We have that code previously right here. So remember, this is in your activity. It's over here showing how to remove the redundant rules. And I've got it right here. I'll pause on the screen for a second, but it is in here showing you how to remove the redundant because we're removing rules. We're only keeping the ones that are not redundant. And then also right here, we are only taking the rules that are significant. Statistically significant, meaning that the relationship we see between them is not likely by random chance. So down here, we're creating it. Verbose, I think we have everything. Verbose false is something that we use to control the output. I'll turn it to true. Doesn't really matter. It's just going to take and show a bunch of output. If you turn it to false, it's not going to show output. So it's just verbose, like it talks to you and tells you all these things, not important. Now be careful, we are calling this length 2, so all of these have to change to length 2. And this is going to remove any redundant rules, so that bye-bye redundant rules. And this is going to remove any rules that are not significant because it's a logical check to see if the rules are significant and going inside of the length 2 list of rules and only taking the rules that are significant. So we basically now have a list of rules that are not redundant and a list of rules that are statistically significant. What does it mean for a rule to be redundant? Like if we had product A, product B tells us about product C, or if we had product B, product A tells us about product C, that'd be a redundant rule because it's do you have the left-hand side? How does it tell the right-hand side? The left-hand side doesn't matter. Rock.
It doesn't matter.
If we do A, B, or BA. So we want those redundant rules removed so we don't have to look at more rules. Okay, given the lift. Let's see, does it give us a check? Inspect these 14 rules. Haha, we did it. So inspect these 14 rules sorted by confidence. So this is once again where we have to do some qualities, and I can't state this enough that these codes right here are found in the notes. If you watch class today, I was going a lot through the notes, and you'll see a lot of different codes right here on how to do it with examples of how to sort your rules, how to do the subsetting. Be very careful because it's easy to make errors, and you always want to check what you create. You always want to be looking at it and saying, is this creating the output I want? Have I sorted these? Have I subsetted these? Do I get what I want? And here we are with the quality of the rules, which we need to analyze to make a subset. So let's go ahead and start doing this right here. And we're going to sort them by confidence right here. We're just going to grab this and bring it down to here. So inspect the 14 rules sorted by confidence. The one with the highest confidence, which isn't that high, is apricot Danish cherry tart. Oh, rules not found. Aha. Because there we go. I'm storing it into sorted, which is fine. You could just sort it. Oh, and then we need to inspect. Now, we mentioned this a lot in class today. As soon as you inspect the rules, you cannot manipulate the output. So there's a very long, very wide thing. We'll rerun it, and there we go. It says we should have cherry tart up here. Apricot Danish cherry tart has 57% confidence. Has this right here. It looks like we're doing it properly, so we're good to go on this. This says if somebody buys an apricot Danish, how does that impact the probability of them buying a cherry tart? 5.3% of people buy both an apricot Danish and a cherry tart. The confidence that somebody will buy a cherry tart given that they have an apricot Danish is 57.3%. The coverage, which is the probability of the left-hand side, which is apricot Danish, is the probability of someone buying an apricot Danish. We could confirm this right here by running this, and we should get 0.092. So if you look right here, this is the frequency of this one, 0.092, which is once again the same as the coverage. We don't talk a lot about coverage, but that is what coverage means, is it's the support of the left-hand side of a rule. Not a big thing. But the lift is super important, and this is what we call delifting. If you take the confidence, which is the new probability, and divide by the lift was the factor increase to the original probability, so there is the original probability, and we can confirm this by going right here and running the frequency we created of the cherry tart. If you notice, there's a bit of a rounding issue, but that's all right. But probably because the decimals weren't carried out all the way on these, because you can only carry so many significant decimals, at least if you're outputting stuff. So this right here is delifting. So it confirms that the original probability of 0.96316 was raised by a factor of this right here. And that is the new probability given someone has an apricot Danish in their cart. Given someone has an apricot Danish in their cart, the probability of having a cherry tart increases by 6.156 times, like a factor increase, not a percent. I almost said percent by accident. And that means these items, another way to interpret this, hint, 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 for your assignment, another way to interpret this would be that the probability of seeing these two items in the cart appears 6.156 times more than we would expect them to appear together by random chance. The combination of items right here in the cart appear 6.156 times more than we would expect via random chance. Let me write this down because it's key to the assignment. So lift and lift. Okay. So here's your two interpretations of lift right here. Why are they different sizes? Are they the same size? There we go. The first interpretation is the probability of right-hand side increases by a factor of lift. Whatever the right-hand side is, fill that in. So, when... And so there is the one interpretation has left-hand right-hand side. So RH, and then the other one would be, the other interpretation of lift would be the two items that list them appear lift times more in the cart together than we would expect by random chance. So change, not chance. So this right here is two interpretations. So if you're in 474, this will definitely help with the assignment because I believe we go into the two interpretations. So you can talk about it as a factor increase or in a Bayesian sense. I think I could help on question 1. Yeah, what's it say? What's it say, Corlin? Good question right there. Question 1 on, so tell me what your quiz question says because each one's different. So we'll do that right here. But there's two interpretations of the lift right there. Awesome, Peyton, great work. And thank you, Peyton. Good questions. Okay, we still got time. Let's do this. What does question 1 on the quiz say? All of the quizzes are usually different. So what does your question? I'm logging into my Pearson as we do this right here. Get my Pearson up and going and do a little quiz 7. Thank you, Peyton, so much for the good 474. Always want to be putting as much interpretation, as much help as we can out there because it just takes practice. It takes a lot of reviewing. I get lucky because I get to review all this stuff. The best way to learn material is to teach it, and then you have to like memorize everything. You gotta be like, okay, I gotta memorize this, gotta memorize that, gotta know how to do this. Let's take a look right here. The question is, suppose the probability of the bus arising. Oh wait, can we do? Yeah, Sarah, which one's that on? Suppose the probability. Okay, so we can do that right here. Classified ads. So we'll do Corlin's question, then we'll do Sarah's question. So here we go. Classified ads in the local paper offered use several cars of a particular model. Okay. So classified ads, several cars of a particular model. And then we'll do Sarah's question next. Let's take a look. Oh, we got this one. Cool. Only got a few parts. Here we go with Chapter 7, Classified Ads. Where's my streaming software? There we go. Here we go. Chapter 7, Classified Ads, 201. Let's do it. This one looks more complicated than it is. You might think you need to run the regression here, but you don't. Here, I'll show you how to run the regression, but this is not required for this one, and I'll explain why in a moment. So when you take this, copy to clipboard. Remember, I'm doing this a little quickly because you don't have to do this portion. I'm going to copy it to clipboard. I'm going to hit Command or Control C to copy it. Then we're going to bring this over here to jump. We're going to go to File, New, Data Table, or Controller, Command N. We're going to paste with column names, edit paste with column names. We're going to go here to analyze fit Y by X. We're going to explain the price of a car by its years, and we're going to make a regression. Now, something I want you to notice is that this has a what relationship. What do you immediately notice about this relationship? It's a different one. Sorry, here we'll do this one, then we'll do the next one. We'll do if there's another one that is like this. So once the scatter plot, okay, cool. We'll do that here next. What do you notice immediately about this relationship? This is a good question right here, and then we'll do the next one. This one won't take that long. What is one thing you immediately notice about the price of a car and the age of a car? What do you notice immediately? Like, oh, okay, wait, that's a what direction? First thing to notice immediately is that this is a what direction. So where people usually make the mistake on this one, it's such a small mistake, but it's such a big mistake. What do you immediately notice about this direction? Should be like, oh, this is a what direction? Negative linear, exactly. Mostly linear. I'd say negative, mostly linear. It should pass. I think it passes the conditions. So when you look at this right here, the correlation needs to be negative. So the way to get correlation from r squared is to take r squared and square root it. But do not forget, once you do this, to take the negative. So you're going to go right here and go negative, and then you're going to go to 3 decimal places and subtract down, and that's it. Make sure to do negative because you can tell if you look at the data, the older cars are selling for less and the newer cars are selling for more. Also, if you do it in jump, you can see it too, but key things right there. It just makes sense. Older cars sell for less than a new car. Next, we have the interpretation of r squared. Blank percent of the variation y is explained by the variation in x. So we have here the r squared value. Advertised price, no. Age accounts for. So age is explaining. If you think X explains, that helps out. They do a little different interpretation. But age accounts for, or age explains about 89.3% of the variation in price. We're trying to understand price, and age accounts for this much variation. Why doesn't this model explain 100% of the variation? They changed this question recently, and I like it. So there's not enough data points in this model. Nothing to do with it. It's impossible for real data to be perfect. That's false. Real data can be perfect. Different. Ooh, this is the one where I get mad. That is theoretically true, but there's going to say this right here. We're not going to get a second thing wrong today. This is the one I get mad about. Yeah, that technically is theoretically true, but this is going to be the answer right here because there's other things that explain not just the age of a car. Let's check out the other one right here. So there's another question. I think you are correct. There's another one that's price and age related of cars. So let's see right here. We're finding the other price and age of cars. And then we're going to do the other question. Here we go. Okay. Here's the other price and age of cars. Classified ads in a local newspaper talk about remember, if you're in class yesterday morning when internet just went crazy and Facebook had problems, Instagram had problems, what's going on? Why YouTube having problems? Did everyone just like come over to YouTube because Facebook and everything are like, I can't be on Facebook, so I'm gonna go over to YouTube. YouTube got a bunch of people. Crazy world we live in. So we need to take this data. We're going to slow it down this time because now we actually need to make a scatter plot. These two scatter plots are the ones we're going to pick from because, like the last problem, the age of a car is going to have a negative relationship with the price of a car. So I'm going to slow it down this time. You ready? Once we go here, we're going to go and click the data table. Then we're going to go to the button here, copy to clipboard. Once we copy to clipboard, we're going to hit Command or Control C. Command C on a Mac, Control C on a PC to copy it. And then we're going to go over here into Jump. Go to anywhere in Jump. You could technically be anywhere. And go to File, New Data Table. Control or Command N. File, New Data Table. Once you're in the File, New Data Table, don't click inside of it. That's the number one mistake people start to make. They say, I'm going to click right inside of that. Don't do that. Don't do that. We're going to, you can click to open it wider, but don't click inside of it yet. You can go to Edit, Paste with Column Names. Now, why are we pasting with column names? There was an age and price at the top of that data set, so we want to paste those column names as the first entry right here. So now you see the column names are pasted. If you did this, restart, rewind the video. If you see this where they're red, there's an error that's been made. You did not paste with column names. Don't try to fix it. Just restart and paste with column names, but don't try to fix it. It takes longer to fix than it does to restart. It is fixable, but takes more time. So now that we have this in here and they're blue, very important that they're blue, meaning quantitative, we can start to do the analysis. The analysis on this will be analyze and then fit y by x, because we're doing a bivariate relationship right here. Now, since we have two quantitative variables, for 200 points in the chat, who knows what kind of graphic we're going to get by doing two quantitative variables and looking at the relationship between two quantitative variables. What kind of relationship will we get? Who knows in the chat? So follow along right here. With two quantitative variables, a quantitative x and quantitative y, this will definitely make this graphic that we're about to see right here. We're explaining the price, or we're understanding the price explained by age. Age explains y price of a car. Scatter plot right there. Hit that 100 button twice. And this is a scatter plot. Great job. I hit all the buttons. Great job right there, everybody. Scatter plot. Yep, two quantitative variables make a scatter plot. So we see the scatter plot. And here's the hardest thing. They really try to trick you with this graphic. Do you see this little dipper up here? And we got a little dipper up here, and then we got a little dipper over here. Now we need to find those little dippers. Let's find those little dippers. And what am I talking about? You ever see the little dipper? It looks like a spoon. There's a little dipper straight up right here. And this is a little cup right here. Okay, do we have the little dipper right here? I don't see it. I don't see my little dipper. Let me look over here. Do you see my little, there's my cup. You see the cup? You see the little dipper? And then we should have a fish hook. I don't know what the thing's called. I don't know. I'm trying to make sense of shapes. And I see it right there. Make sure you see the same patterns, and you should see the same patterns. I can almost get them all on the screen at the same time. There we go. Now I can, if I do it. Make sure you see the same patterns, and you will see the same patterns. There's the cup, there's the little dipper, and there's the fish hook. So we got everything we want. The other graphic will not look like it, so we have achieved the same graphic. Good to go. I think this is if you reverse the x and the y. Don't do that. The association between age and price is... it's negative. Definitely negative right there. And is linear. Let's go with linear. That's linear. That follows a line. Is something linear means does a line go through it? Here, watch this. fit line by going to the red arrow where our options are at, and does a line well go through the data? Does it perfectly go through? Nothing perfectly goes through. Mostly linear, I would say. Pretty good linear, no real outliers, and it is very strong. Strong is how tight it is around the form. It has a linear form, and we can see how strong it is around the form. And we could calculate things like the correlation. It doesn't ask us to calculate correlation, but correlation would be square rooting the r squared. So we take the square root of this, and then we have to do the negative. So that is the correlation right here, negative 0.945. And that's super strong. That's very close to 1, which is the strongest linear relationships we can have. Or negative 1, because this is downward. So do you think linear model is appropriate? Q straight enough. No outliers. Plot doesn't thicken. Doesn't matter. We don't randomize our data. So the linear model is appropriate because the data are relatively straight and there's no outliers. And it's a scatter plot. So Q straight enough. No outliers. Plot doesn't thicken. Oh, and then we got to find the correlation. Well, we did it. Square root the r squared, but do not forget that when you square root it, you must check the direction. That's on your Canvas content. So when you square root it, you must check the direction. And then we're just going to round to 3 decimal places. Explain the meaning of the r squared. So right here, it's the percent of variation y explained by the variation in x. So a linear model on age accounts for 89.4% of the variation in price. We're trying to understand price, the variation in price, and age explains or accounts for. They use the word accounts right here. I would say 8, 9. I know, right? Kayla right there, 100 points. It's good practice. Trevor, good to see you here. It's almost like we did one just like this. No, don't worry. Excellent questions. Oh, we're missing one. Why doesn't this model explain 100% of variation? Let's see right here. Other factors. Okay, good stuff. The age are rounded to years. It doesn't matter. Is it impossible to explain over 90%? No, we can explain a lot more. The data contain more than 10 points. That's such weird answers. Yeah, I think they changed this one. They change things around every once in a while, and then it'll make me go crazy. But good stuff right there. I think we have time for the other one. Sarah's question was, suppose the probability. This is a tough one. It's from a Canvas content, I think. Let's go check it out. Wrong button. Last question of the day right here, I think, because we'll be preparing for class here in a moment. Grab a little more food. Tough stuff. Yeah, Corlin, great job. Thank you so much, Corlin. Another 100 points. Thank you for being here. Thank you for asking those questions. Just the practice. Like, the more you practice these things down and be like, okay, when I have r squared, it's correlation squared. So if I square root it, I need to check the direction of the plot. Just repeat those things. And the more you do it, you get to the test and you're saying, oh, that's an r squared. Let me square root it and check the direction of the plot. You get to questions, you'll be like, it's easy one, I got it. That's what we want you to do when you get to the test. I might have time. Trevor, throw it in the chat. I might have time. I'm going to try. I teach in 27 minutes. No, I might want to grab some food. Throw it in the chat, Trevor. We'll see what we can do. We've got a chapter 12 question. Chapter 12 question. Okay, let's look at a chapter 12 question here. This is not an easy one. One of the toughest ones. Chapter 12, dealing with the complement rule and the multiplication rule. Let's check it out. So this is a chapter 12 question right here, and it's pretty tough. But practicing it makes it pretty easy. I'll solve it. You ready? Suppose the probability of the bus arriving on time is 0.5 for the next 5 stops. What is the probability the bus is on time for at least one of those stops? So the probability... Oh man, it's going to be really tough. 2 seconds. I'm going to solve it in my head right here. So the probability is 0.9675. That's the answer to the question. So how can I solve this in my head right here? I think we can do that. I think we got time for that, Trevor. What's up, Trevor? So how did Brian solve this in his head? Let's talk about what's going on right here. We have a bus right here. Let's take a look at this bus. Would you agree with me? There's 5 stops. Make these stops all symmetric right here. With the 5 stops for the bus, what could happen at the next 5 stops? I was kind of doing something like that, Sarah, kind of. So we want to know, what is the probability that the bus is on time for at least one of these stops? So the bus right here could be on time. Just think about this. It could be on time for all the stops. So if you've been doing this chapter, and we'll be going more in depth in this is maybe a quicker explanation. What is the probability the bus is on time for the first stop, the bus is on time for the second stop, the bus is on time for the third stop, and the bus is on time for the fourth, and the bus is on time for the fifth? If you've done this chapter, you know Brian's using the what rule to solve this right here. This would be the probability the bus is on time for all the stops. So the probability it's on time for each stop, and assuming their independence, it says assume independence, which is key. A key assumption for the multiplication rule is independence to multiply things. You must have independence to multiply. We will be reviewing this, and people oftentimes confuse the two rules, but I'm not going to mention the other rule right now. It's the addition rule. But a key assumption here is independence, which you might even argue we might not have it for this. But what is the probability the bus is on time for the first stop, and the second stop, and the third stop, and the fourth stop, and the fifth stop? So you might say here, Brian, but it doesn't say that it's on time for all these stops. It says something completely different. It says, what is the probability the bus is on time for at least one of these stops? But you could find out the probability the bus is on time for all these stops right here, like it's on time for the first and the second and the third and the fourth. What word do I keep saying instead of saying multiply by? I say the probability it's on time for the first. Three-letter word I keep saying, which is synonymous with multiplying right here. Like the probability it's on time for the first, probability it's on time for the second, probability it's on time for the third, probability it's on time for the fourth. I keep saying what word between these. Might have time for that one. We got 24 minutes. I'll take a look, Trevor. Might have time, or I might send you a video. I keep saying and. Sarah, great job right there. So that's the multiplication rule here. Very important to know when you're multiplying to get things together. They must, let's put a note right here. When multiplying, I'll increase font in a second. Things must be independent. And we say and. So when you look at the and coming out there. So when we multiply things together, which is the multiplication rule right here, things must be independent, and we will use the word and. Key stuff right there. But this doesn't talk about what's the probability all of them are on time, which we could find out pretty quickly by going here and going 0.5 times 0.5, 2, 3, 4, 5, and that's the probability every bus is on time. It says something a little bit different. It says, what's the probability that the bus is on time for at least one stop? So we could start getting into that, because here's the thing. Let me ask you this, and this will help solve the question. Can you tell me what the probability would be that the bus misses every stop? What's the probability that the bus misses every single stop? So now we're saying it misses the first and it misses the second. So if it has a 50% probability of being on time, what's the probability it will be late for a random stop? So now we're saying what's the probability it's late for the first and late. This is where you're seeing it. It'd be the same, so the probability of late, so we'll put here probability of late is this, and then it would just be the same mathematics. So this is the probability it's late for the first and late for the second and late for the third and late for the fourth and late for the fifth. So we just solved that too, and it was the same mathematics we just did. But tell me this. The bus, and here's where the big thing comes in, and we're actually doing the addition rule of sorts. This is the big trick to it. The bus will have two possible outcomes. The bus could be, let's say, late to 0, 1, 2, 3, 4, or 5. What's probably the bus is on time? Oh, no. The bus could be on time to 0 stops, 1 stop. Keep hearing like knocking. What's probably the next stop? The bus is on time for at least one of those stops. So the bus could be on time for 0 stops, 1 stop, 2 stop, 3 stop, 4 stops, or 5 stops, right? So what we just found right here is the probability the bus is on time for how many stops. So we did it's late, it's late, it's late, it's late, it's late. We just found the probability the bus is on time for how many stops. Be careful. We did, it is mathematically that too. But if we say the bus is late and late and late and late and late, this is the probability the bus is on time for 0 stops. Just describing it this way, does that make sense? It's mathematically the same as the 5 too. But this is the probability it's on time for 0 stops. So now that we have the probability it's on time for 0 stops, which is 0.325, to 5, it'll either be on time for 0 stops or it'll be on time for at least 1 stop. And who remembers the word for 100 points of what we would call this? Kayla, this is a review now. This word right here, which is giving someone a nice thing, saying a nice thing. I don't want to say the word, but this is the what of the probability which is found, which you can see I found it up above. So this right here, this thing that we can find to say, well, it's either going to be late for all the stops or it's going to be on time for at least 1 stop. Kayla right there, 100 points. That's the complement right there. And so this is what I did. So I had to do 0.5 times 0.5 times 0.5 times 0.5 times 0.5. And then I found the complement of it to say it's either late for all the stops or it's on time for at least 1 stop. This is a tougher problem. But if you practice them and get them down and write down your work and show it, use the rest that wasn't exactly. It's the remaining portion. Because either it'll be late for all the stops or it'll be on time for at least 1 stop. So this is where it's on time for 0 stops. This is where it's on time for at least 1 stop. Because either it's on time for no stops, which means it's late for all them, or, and this is the addition rule, because I'm saying or, because you could add these together. And what do you get when you mathematically add these two probabilities? You get 100%, because they are disjoint, which is the rule for addition. This is a very good review of something we have not gotten to yet. Pretty complicated stuff. And we'll put this down here on the bottom. But if you followed along with this, this is kind of an introduction to you. We do this right here. When adding things together, must be disjoint, which is the same thing as saying mutually exclusive. And we say the word or. So you can hear my terminology down here. Yeah. And so this is a good introduction to it right here with one of the most complicated questions we could do. So I can say the bus is either late every single time or it's on time for at least 1 stop. And last question, I will throw 500 points again. I've listed all the possible outcomes. This is the what of what could occur. Take a shot at it. Just try to remember the terminology. This is all possible outcomes of things that could occur. We would call this the what of events. This, like, it could be on time, it could be late, it could be on time 0 times, on time 1 time, on time 2 times, on time 3 times, 4 times, 5 times. We call this the what right here. The sample space. Kayla, great terminology right there. That's the sample space of what could occur. And that's what it means. Like, here's, so that's it, 500 points and excellent work. Great job. I think, do we have time? So excellent work. Just practice. It's learning the terminology. That's everything that could occur. It's the sample space of possible outcomes of events. Woo! Let's go back to the main screen. I think we got time. We'll try to do it quickly here. Might have to send a video. You're welcome, Sarah. That's a big question. We haven't gotten it to yet, and I'm probably going to put that towards the middle of next week, making sure we have enough spacing. A lot of work. So much work. Start with the wrong. I need the group of high school student aptitude test. Is it the SAT thing? We don't have time for that. Trevor, message me and I'll send you the video on it. Because I think it's... Is it the group of high school students? If it's the SAT one, we don't know about that. I'm going to grab some lunch real quick in a moment. Oh, no, we might. We'll do this one. Let's do it. Okay, we're going to have to do this quick here. Let's do it. Let's knock it out. Here we go. Hopping in here, a group of high school students. Let's do this. Let's make it happen. Oof. Okay, so we're going to use the regression solver for this. So I'm going to do this one a little bit quickly, Trevor. So sorry if I go quickly here. I'll be teaching in 16 minutes. So I want to do this in 6 minutes. Quick solve on this question to end office hours today. We need to get the regression solver. Project is posted right here. I don't know why that's not a link. I need to change that to a link. So the regression solver is found under the modules. And we're going to go here to modules. And we're going to go to our regression solver pro. Love it. And the regression solver pro is going to solve a lot of these things for us, taking the information we need. This is under the modules, the regression solver pro right here. And so we have everything we need with the regression solver pro. Awesome. You're welcome. Excellent work, Kayla. And so there's the regression solver pro in here. And let's take a look at the question. So the correlation right here, what is the correlation? The correlation, it's got to tell us. Oh, it's literally asking, what is the correlation? It's literally telling us it. So it just wants you to acknowledge it, basically. So there's the correlation right there. And then we are making a model to predict what? Predicting verbal. So verbal's the y variable. So verbal is going to be the y. And so with verbal being the y, let's make this so we can see it all. Remember, verbal's the y. That's key to this question right now. Verbal's the y. And so now we've got our Regression Solver Pro, which I would highly suggest using. I'm going to display off the screen. And the correlation, there's the correlation. Verbal's the y, so we want the standard deviation of verbal. Math scores, yada, yada. And verbal scores had a mean of this and a standard deviation of this. Be very careful. Verbal is the y. And so the standard deviation of x, 202.3, one error, and you're going to make a mistake. That's the mean of x. Remember, verbal is the y, so we want the mean of math. And you would not solve these on the test. That's why we would use the regression solver here, because this is just carrying numbers and decimals and much easier. We get the intercept right here. This is the intercept value, round to 3 decimal places. There's 3 decimal places. And next we get the slope coefficient, and it is a positive slope, hence positive correlation, round to 3 decimal places right here. So we should be good. In general, what would a positive residual mean in this context? So when you think about a positive residual, someone has an actual score higher than their predicted value. So a positive residual would mean that the student has a higher verbal, I believe so. Yeah, because then the linear model would predict. They're above the model. So residual is how far are you above or below the model. If they have a 0 residual, they'd be exactly on the model. A person tells you that the math score was 285, predict their verbal. Once again, we're just going to plug in 285, but we should probably do it this way. I don't know. We're going to use this right here, 285. So we're going to predict their math score, and we're just solving via the model because it just makes predictions for us. As long as we carried our numbers properly, we should be good. Round to 3 decimal places is good. Using the predicted verbal score from part D. Ooh. And the regression equation, wait, what? Predict the student's math score. Really? Really? That's weird. So now we're doing the predicted math score. Yeah, okay, so we're going to use this. That's a weird question. Please tell me I don't get that wrong. It's just something you wouldn't do. The next question is like going to get into that and be like, you wouldn't do this because this is like not how the model works. Ooh, look at that. We're going to make errors. So it should be a little bit bigger than that. Okay, it does. And then we want to subtract because that's a negative. You add a negative, it's going to subtract it. That looks good right there. Why doesn't the result, the line found in part B minimizes squares in the math direction, while the line in part E minimizes squares in the verbal direction? Oish. Theory question. Okay. So we're trying, the line in B is predicting verbal. The line in part B minimizes verbal direction. Okay. Are these just reverse? The line found, yeah, you didn't, look at this. The line given in part E minimizes verbal, no, it's minimizing math direction because it's that variable. Should be right. Oh, that's such a weird one. Woo! Yeah, that's a major theory one. The sums of squares are the residuals, and so you're making predictions. The residual squared is the squared error. Major theory question, which goes a little deeper, which I don't think really helps with the interpretations. But that's got it. 12 minutes till teaching. So got this one done right there. Tricky question at the end. And also, oh, did it actually accept this? Ma Pearson, you're my new best friend, Ma Pearson. Little positive. Thank you, Ma Pearson, for not being mean to me. Trevor, have a great day. Trevor, thank you for being here. Excellent work. Teaching here soon. Yeah, it's that you're minimizing the sums of squares is the error on the y variable. So you're trying to make as little of an error, trying to reduce the residuals. And that's what a sums of square is. Go into more detail in 320 on it. Even I had to pause for a second and say, like, which is the y variable? You just say, we're trying to make small errors. The model's doing this equation. But that's got it. I'm going to head off here. Bye for now, everyone. Bye.